Can you all hear me okay? Hello, can you hear me?
Yes, sir.
Okay, yeah. Great. And if you want to turn on your cameras, great. It'd be better for me, but I do understand, especially if it's lunch time. All right, let me go ahead and share my screen first. All right, hopefully, everybody can see actually this thing, but what I wanted to do is ask you right now, did you have any questions about any of the homework? For starters, I had one question on another Zoom meeting from somebody. Anybody at all? Because this is power factor correction. It's important, but it's fairly simple and straightforward. So any questions first? Y'all can hear me, can't you? Right? You just gave me an affirmative. Okay, and if you want to turn on your, oh, wait a second, Jessica, warn me next time you're supposed to be a co-host. Anybody else want to be a co-host? Got you, Joseph. Turn on your cameras if you can, if you don't mind. And anybody wants to be a co-host or anything like that. Now, this is the stuff you have to keep up with because cramming for this is virtually impossible. And I can reference in your books where this is actually discussed, if you'd like. I try to do this on the overhead in class because I think I can make it a little more clear. And I do have a PowerPoint that I can reference that I posted about this. I can post another one. But what I want to do is talk about power factor correction. And I'm going to go through a few problems. And if somebody has one, I figured I'd get a bunch of questions. But since I haven't, I'll just assume.
Sorry. Dr. Baginski, can you do 5.36, I think. Yeah.
36. I'll be happy to do that. First, I want to just review the basics, okay? Mm-hmm. With everyone. So in general, if you have a load here, this is the basics. And believe me, we're going to move a little faster in the next couple of days. And here you're going to have some voltage. This is the load right here. Some V load right here. I'll just call it load. And we know that this has some magnitude and angle of voltage. Usually this is some magnitude V RMS right here at some angle, theta, but that angle is usually 0 degrees. I'll call it theta V. Then here you're going to have something that has a real power. It has some impedance Z and then it has a real power, P load. And the units of this will be kilowatts. It also has a power factor. And we know from this information, we can always get the current in the line or load, whatever you want to call it. So I'm going to take you through this so everybody sees this. So for beginning, if we're given P load, let's assume that we're given P load. The next thing we can do is find I load. And we do that in terms of the magnitude by saying it's P load divided by V on the load, that's the load voltage, and times the power factor. Now that gives you the magnitude, maybe I should put it like that, the magnitude of I load. Third thing, you find the angle of the current I load. And that angle, I'll call it theta right there, I load, will be equal to a cosine, inverse cosine of the actual power factor. Now that's usually in radians. I would recommend you put it in degrees. If it's lagging, it's minus. That would be lagging. And if it's leading, it would be plus. All right, so you can get the current. Now you have the current and the angle, correct, class, so far? Now what we do is construct a complex power diagram. We define complex power as V, and this is for anything, but in particular for the load, V times the load. And here that's going to have a magnitude and an angle. And then it's times I in the load, but it's conjugated. And that's the key. Conjugation always flips the sign of the angle. Now, when you do that, you draw a power triangle. And I hope you all can see this. The power triangle have the real value of the power on this axis. This will be actually the P in the load, and the units will be kilowatts. Then you're going to have an imaginary term, and if it's lagging, if the current's lagging, it will be in the first quadrant. And this is going to be given as JQ, and that is actually the reactive power. And the units, this is reactive power. And the units of this are in kVAR. I'll explain that. It's K is 1,000, so 1,000 volt amps. The units are volt amps in both power and the power actually dissipated, or real power. This is often called real power. Or in the imaginary power, reactive power. All right, it's kVA, but the R at the end means it's reactive. Then you get something here. This is actually S complex. And it's got a real and an imaginary part. This angle here is actually the cosine of that angle, actually. The cosine of that angle is the power factor. Now that's it in a nutshell about how you take a look at a single load and look at it in terms of a complex power with both a real power and a reactive power. Are there any questions about that? That was part of what we discussed last time. Everybody got that? It's pretty straightforward, right? Can I get some kind of an affirmation? I'm looking at one person.
I'm still writing it down.
Yes.
Oh, Jenny. All right, Jeannie, thank you. That's okay.
Where you wrote SC is equal to V load, is that a minus in between I load and V load?
This is a multiplication. It's V times I conjugate.
Gotcha, thank you.
And I'll try to make it a little clearer. Now that's not going to help. And please ask questions. S complex is really, in general, V times I conjugated. Now, V is going to have a magnitude and angle. I will have a magnitude and an angle. And that is the complex power. Now to correct it, remember, this is the original power factor. And you can call this PF and then old if you want. And it will result in an angle, theta C old. It's the old angle associated with the power factor. And in general, when we put a capacitor across this, last time I talked about this, the capacitor itself has no real power dissipated. So that capacitor has a reactive value, a Z value of really 1 over J omega C. And therefore, if we put a load across here, voltage, V, can be anything. Let's make this V at an angle of 0 degrees. Then the current through the capacitor, I sub C here, would be equal to V at an angle of 0 degrees divided by that impedance, divided by 1 over J omega C. Or it would be equal to just J omega C times the voltage. And since the voltage I'm assuming is at 0 degrees, the current through that capacitor would be at 90 degrees. You all agree with that, class? Just some affirmation in general from anybody. Thank you. Thank you. Brandon, you're gonna, thank you, Jess. Anybody else? Are you guys with me? All right, now, please hear me on this. This is important that you listen. Now, when we go ahead and get the complex power associated with this, and I can call it of the cap, but it's really just going to be minus J something. That complex power is V at an angle of 0 degrees times I conjugate. Well, the conjugate of this would change the J to minus J. This is J is really 1 at an angle of 90 degrees. Conjugated would be 1 at an angle of minus 90. So it really would be minus J omega C times V. And because that's 0 degrees, this is really minus J omega C times V squared.
You're writing outside of what we can see.
Thank you. So it's equal to minus J omega C times V squared. Now this is the complex power associated with the capacitor. Does everybody understand me? Everybody's writing some affirmation, some way of me knowing that you understand. And the more the better. I don't know how many people are actually here or on.
Wait, so is this the reactive power of the capacitor or
Yep.
the total?
Yep. Well, you can see it's just the capacitor because I only have a capacitor here. Is everybody good with that? That is only the reactive power of the capacitor. And here's the idea. We only have 52 on here. I hope there's multiple people looking at a single screen. Now, here's the deal, and this will get complicated if you don't listen. By adding this reactive power, you'll notice that minus J, right? So if we were to plot that and superimpose it here, it would be down here, wouldn't it? That'd be minus J omega C V squared, right? Everybody? How many see that? I'll do your problem, Jessica, and I'll do any other problem, but I want to make sure you all see that. Thank you, Jenny. Anybody else see this? Hunter?
Yes.
Okay, thank you. I really wonder, I hope there's a lot of people on here because this is going to be something on Friday's quiz and it's important you see this. Now, if you see that, then you can see when I add this plus this, it'll be reduction in the net length of the imaginary, the JQ term. Does everybody see that portion? Think about it. Minus J omega V squared, CV squared. And here it's a positive value, right? Okay. We'll do a problem with this. So when you add this to this, it'll reduce that. And what you're left with is this. So the new power triangle, this is new with C added. What you'll have is this. You'll have the same real power. So the actual P and the load will be there. It will not change. But now the reactive power here is going to go down. And it will be its old value, and I could call it JQ and then just put old, but it'll be minus omega C V squared. It'll reduce that, thereby making this angle smaller. This would be theta nu. This is the idea. How many understand at least the concept of adding a capacitor to reduce the complex power at the load? I shouldn't say that. To reduce the reactive power at the load. Doesn't do a thing to the real power. You with me? So it's getting the power factor closer and closer to 1. Go ahead.
So are you adding this in parallel or in series?
Always in parallel. And what it would be is like last time when I showed you, the capacitor would go right here in parallel. Always in parallel, never in series. Okay? Now the best way to see this is do a problem. So I'm going to do a problem. This is, I think, the fewest number of students we've had, but I'm going to do it, and I'm going to start with a problem that you asked about, Jessica. It's 536. So for 536, it says an industrial load at a frequency of 60 hertz. So it's just 60 hertz, which means omega is 2 pi times 60, 2 pi f, or it's 120 pi, and that would be radians per second. Here again, I'm assuming that you're familiar with the concept of omega as well as f. Next after that, we see we have a load of 100 kW, so draw it. You'll notice there's nothing in the actual line, no impedance yet in the line. And we have a load here that's going to consume some load here, an actual power in the load of 100 kW. Right? Then it has a power factor here of 0.7 lagging. And then it has 480 volts at 0 degrees here. So the voltage here is 480 at angle is 0 degrees. And if a 100 microfarad capacitor is placed in parallel with the load, what is the new power factor? Well, we're going to first calculate the old power factor without adding that. Everybody got that?
Yeah.
I'm not going to put the capacitance. So first thing I need is this load current. And I'll just call it IL here. Well, to get IL in magnitude, I know what I'm going to do is simply take this 100 kW, right? 100 times 10 to the third. If you have calculators, and I've talked to a couple earlier today, please just give me the answer. It'll save me time from pulling up octave. Then I have to divide it by 480, right? That's the RMS voltage. Then I have to divide it by the power factor of 0.7. Do you agree with me, everyone?
Yes.
The silence is deafening. Okay, thank you. What's that value anyway?
297.62 or 619. I don't know how many decimals you
6.2 is
want.
fine. How many else got that, or how many other people got that?
I got that as well.
Yeah, I got that.
Thank you. Please use your calculators too. Problem is the chat. If you're on chat, somebody, it's important to tell me because it's obscured. It's behind the screen I'm looking. All right, that's the magnitude. And the angle is what? What is the angle associated with this kernel or this current? It would be what? Minus, and it would be what? Cosine -1 or a cosine of 0.7. What is that? 36 point something degrees? Anybody? Can you do an inverse?
45.5.
45. 45 point what?
5, yeah.
Minus 45 point something, right? We'll just call it minus 45 degrees.
0.57.
All right, 0.57 degrees, about 45 degrees. Agreed, class?
Mm.
So that's the angle associated with this current. Now, when we find the actual complex power, this is going to be the old complex power. That's going to be the voltage times the conjugated current. So the voltage is just 480, right? The angle is 0, so we don't need to do anything with it. The current was 297.62. And the angle was minus 45.57. When we conjugate it, we get plus 45.57 degrees. Do you agree?
Yes.
All right, now we draw the power triangle and put old here. This is the old power triangle. When we draw the power triangle, we're going to have the real power on this axis. This is the real power, which is 100 kW. Then this is the angle, which will be 45.57 degrees. And this is the complex power, which is going to be the magnitude of these two multiplied together. If somebody can give that to me, I'd appreciate it. It's greater than 100 kW, that's for sure. It's about 140 kW, somewhere in that neighborhood. Anyone? If you got your calculators at home. You want me to get an octave out? I'd prefer not to. Anybody?
It
Or I got-
is 142.857 times 10 to the 3.
All right, we'll call it 142 K. It's really, this is just kVA. The units of this is kVA, the units of this is kVAR, and this is just kilowatts. So this is watts down here, or kilowatts. This is kVAR, and that's kVA. Now, to get Q here, this is JQ, old, right? Well, to do that, we could say what? Q old is equal to, think about, you can do it a few different ways. I like just doing it this way. Opposite over adjacent is the tangent of that angle, right? Q old over PL is equal to tangent of 45.57, or really Q old is equal to 100 kW, right? That's old. PL times the tangent of the angle, right? And that would be 100 or 10 to the 5th times the tangent of, what is that, 45.57 degrees. Can somebody give me that? Anyone? That would be, that's Q old. The symbol Q and then OLD. Anyone? Luckily, now if you got it, go ahead. I'll get it right here if you just give me 1 second. I was dealing with this earlier. So Q old for this problem would be equal to 10,000. That's 100,000. Better yet, 10 to the 5th, and then times. This is MathCAD if you're wondering what I'm using. Times the tangent, and that's really about pi over 4, right? 44 degrees about. So Q old, I'm getting that. It's about the same. I guess if I was exact about that, I'd get a slightly different answer, but I got about 10 to the 5th for Q old. So that makes sense. It's a 45-degree angle about. So Q old is really about JQ old is J times 100,000 roughly, right?
Yes.
It's kVAR, or 100,000 kVAR, or 100 kVAR, pardon me. Now, what we want to do is reduce this. We want to reduce this. So the next thing we do, and this is going to be to get the new thing, we have to take a look at what they actually want. Now, when we draw this, we're going to redraw the power triangle, but according to the new formula. So what he wants is, by the addition of a capacitor, he wants this. You'll always have the same amount of real power. So the real power here is still 100 kW. Now, we're going to get the new angle. He says the new power factor, we're going to add a cap to get this.
We need to look at your dot cam again.
Yeah. We're going to add a capacitor in parallel to this right here to get this. But first, to get the value of that capacitor, here's how we do it. We take a look at first the information about the new power factor. It's equal to P new, power factor new, was equal to, I'm sorry, we got to calculate the new power factor with a 500 microfarad capacitor. So we're actually going to calculate this new power factor. So what we have to do is calculate, this is the old value of the reactive power. Now we're going to find the reactive power associated with that capacitor and add it in. Well, the frequency was at 60 hertz, right? That means omega was 120 pi radians per second, right? And that means the reactive power associated with the capacitor would be equal to, and you can call this S capacitor, would be minus J omega, which would be 120 pi, right? That would be omega times C. And the capacitance value was 500 microfarad. I'll just put C down here, and that's times V squared. Well, C was equal to 500 times 10 to the minus 6, that's microfarad. And V was 480, right? So V is 480. So therefore I can calculate this, and I'm going to go ahead and do it, if you're okay with that. I'm writing it down, but I'm going to still calculate it.
What is the unit for F?
Frequency is hertz. And frequency is like a wall frequency, 60 hertz. So here I have F equals 60. Oy. Then I have down here, this is for this problem, I have omega is equal to 2 times pi times F. You can change that if you want, but it's no reason to. I mean, if you want to try a different problem. Then after that, we have V here is equal to 480, right? Keep going down. The next thing we're going to do is get complex power associated with the cap. And that's going to be equal to minus 1J times omega times C, right? Times V squared. So that's that. The I is like a J in this MathCAD program. And after that, what I'm going to do is find the actual, this is a Q value there. It's all reactive because of the J. Now I can find Q new, right? Well, that's Q old, which would be really 1J times Q old. It's about 10 to the 5th. It's that minus, and then it's going to be the reactive, or really just plus, pardon me, plus reactive power associated with the capacitor. Now, usually that's actually, instead of S, they'll have Q, but I'm putting an S there because it is a complex power. So the new value would be, wait a second. C on this one was 500. It's 500 microfarad, right?
Yeah.
All right, this would be the new value of Q new that I get, 56 kVAr. Do you all agree with that? Thank you. Everybody? Okay. And I'm just calculating by adding Q old, which was right here, and there is a J associated with that, to the reactive power associated with the capacitor. So you get this. It's 56.57 kVAr. So here we have 100 kW. That never changes. That's the real power. By adding that capacity.
.chem isn't up.
Thank you. By reducing, by adding that capacitor, the actual complex power, or the power factor, is going to get better, or this angle is going to get smaller. Because now, before we started out and we had, if you look at the original, we had this to be equal to J 100,000, right? And that would be VAR. Now it's going to be reduced to simply J here is going to be 56.7, right? 0.7 K VAR. Do you all agree with that, class? Okay, 1, 2, 2. Anybody else? I got 2 out of a whole bunch of blank.
So
screen.
are we, for the kVAR, are we just dividing?
Not dividing,
Or
subtracting.
are we converting to the per 1,000 units? So,
Well, K is 1,000. I could put 56.7 times 10 to the 3rd VAR, or just put K to represent 10 to the 3rd.
okay.
That's the only thing I'm doing here. Y'all agree with me? Now, what's the new power factor? Well, it's still in the first quadrant, right? That means it's lagging. Complex power in the first quadrant would be lagging. If it was in the fourth quadrant down here, then it would be leading. Are you with me, class? Like a capacitor has a minus JQ, right? And you can see if that's added to really any real power, it would have the angle itself, or I should say the vector for complex power would be in the fourth quadrant. Getting back to this, what's the new power factor? Well, we did this angle, right? Y'all with me?
Yes.
I hope you. This is the fewest people I think I've been interacting with.
A lot of us, I don't know, for industrials, I think a lot of us had exam today earlier in
Oh,
the
they did?
morning. It might have to do with that.
Okay, it probably does. Anyway, this is the new angle. So that means, how do we calculate that new angle? What's the easiest way? Just by looking? That's a right triangle, right?
Tangent.
Right. Opposite over adjacent is tangent of that, right? So if the opposite over adjacent is tangent of that, if I want that, I would take the inverse tangent of that over that. So it would say theta nu, let's do it together, would be equal to tan minus 1, right? The inverse tangent of 56.7 divided by 100. Because I'm just using the k's as 10 to the third here. Are you with me, guys? I got one. If you're writing up, I'm just trying to have a meaningful conversation with a blank screen. It's very odd. What do you get for that before I get it? And you can give it to me in degrees, anybody. You all got your calculators, right? Hello?
Yeah.
Okay.
It is 29.55 degrees.
It's about, and by the way, you don't have to be exact with this. Get it in the ballpark, 29 point something. Agree, class? All right. Now that's the new angle. What's the new power factor, anyone? Anybody? Anybody at all? And I appreciate any comments, interaction. Well, what do we do with that angle?
0.86.
Wait, what are you doing though? Say what you're doing, please, Joseph.
Cosine of the new angle.
All right, that's so important that you say that, and everybody's, because some people will be afraid to even ask this. It's the cosine of that angle, correct? That's the power factor. And it will be lagging if it's in the first quadrant. It will be leading if it's in the fourth. Everybody with me on that?
I thought you said it was the opposite. Did I just mishear that earlier?
No, this is the actual complex power, right? The angle associated with the current, if something's lagging, the current would have a negative angle, right?
Mhm.
All right, but when you take V times I conjugate, conjugation puts that negative angle and makes it a positive angle, doesn't it?
Okay, yeah.
So whoever's asking that, so if it's in the first quadrant, if it's complex power, not current, then it is lagging. If it's in the fourth quadrant down here, and again, I'm going counterclockwise, 1, 2, 3, fourth quadrant down here, then it would be leading power factor because the current will be leading the voltage. Okay, whoever asked that or said that?
Yes,
Good?
thank you.
Sure. All right. Now, that said, this is one where they gave us a capacitor. We just figured out what happens when you have a capacitor there. You first calculate the power triangle before you add that other thing, the capacitive value, and then you add it in. Do y'all follow me? Now, some people will say, well, you don't need to do that. Just do it all at once. If you feel that way, go ahead. Just add them up. I wanted to break it down like this because we're going to basically most of the time calculate the value of that capacitor. I want to do another one. Does anybody have a preference? Because I have one. All right, I'm giving you another second. Does anybody have a preference? How many people are on here right now? Because I can't.
50.
Only 50. Wow. I got 8. There's 8 things in chat, and I have no idea what it's about yet. Okay. Anyway, if I can help with the chat, let me know. I just took a peek and I saw. I think most of that was settled. All right, so what's the power factor? Say it again, Joseph.
0.87 lagging.
0.87. It's so important to put lagging. Make sure you do that on a quiz. Lagging. Okay, got it? Now that's complex power. Now we're going to do one. We're going to add a capacitor to reduce the power factor. And we can reduce it to any value. Ideally, you would want the angle to be 0, right? That would be a power factor of 1, whereas where every industrial engineer would like to operate. I mean, that's the ideal. I don't really know right now what the state of the art is. Usually everything you're doing is you're either switching in large capacitors or taking out large capacitors. And it's more or less discrete values of capacitance. So you never get it exactly to an angle of 0 degrees and a perfect power factor, but you get close. That's the reason I think a lot of these problems don't bring it down just to 0. Let's do one, and I'm listening. If you got one, let me know. If you don't, I got one for you. Okay, I got one for you. I'm going to do, I'm going to do 34. I did 32 prior with some people. I'm going to do 534. All right. So the very first thing you have is 75 kW with a power factor of 0.84 lagging. Draw it.
Paper chip.
Yeah. So what I'm going to do is just redraw. Oh, I'm sorry, not 37. 34, pardon me, 34. So for 34, I have a 75 kW, the real power being used. All right, I have a power factor here of 0.84 lagging. Then I have 220 volts here. At 0 degrees volts. It's always RMS. And frequency here is 60 hertz. Determine the value of the capacitance, which when placed in parallel with the load will raise the power factor to 0.94. So this is the old power factor, and you can put it as PF old equals 0.84, and it is a lag, and that corresponds to a certain angle that we'll get. And they want a new power factor of 0.94, which corresponds to a new angle, right? Let's go ahead and first, I'm going to draw the initial power triangle, and we'll use that information. So when I draw the initial power triangle for this, and if you've done this, you may be bored, I understand. First, start with the 75 kW on the real axis. This would be the real axis. So I come out here and I put 75 kW. Then I take a look at this and I know that I have a first it's lagging, it would be in the first quadrant. Power factor of 0.84 has an angle of what, people? Anyone? Here, I'm not even going to bother.
32.86.
0.86. Now the current itself would have a minus 32.86 degrees associated with it with respect to that 0 degrees for the VRMS. But the actual complex power, and this is the S plane, because S complex is actually equal to V times I conjugated, the angle would be in the first quadrant, and it would be looked at as positive because of conjugation. So here we're going to have this angle, theta old, right? And we find the complex power right here. And that JQ value would be what? How would I get that? Well, wouldn't I say that the Q value here, and you can call it old if you want, would be equal to what? The 75 kW times what? The tangent, right, of theta old. Or that would be 75 times 10 to the third times the tangent of 32.86 degrees. Do y'all agree with that, class? So
Yeah.
what is Q old? Just give me the magnitude.
got a value of 48.45.
Okay, 48.45 K var actually, right? Or 48.45 kVAR, kilovolt amps reactive. Agreed, class? Thank you. Was it Tanner? I think, I'm not sure. So that's 45.45, right? Now we could calculate this right here. It's just this plus this, right? It's real 75 times 10 to the third plus J 45.45 times 10 to the third. We could, we don't need to. That's the old, right? This is the old thing. What do we want to do for the new? We want to add a capacitor right here, right? We want to find the value of that capacitor, so we knock it down. Now, the capacitor itself, again, I'm going to restate this. The capacitor itself has a complex power of minus J omega C times V squared. That's what that complex power is. Give yourself a second to write it down. You good with this? Okay, now what I'm going to do is add that into the system and calculate the value C, but I want to add it in such the new thing looks like this. The new power triangle or complex power triangle. S new will look like this. It'll have the same real power, always will, which will be 75 times 10 to the third here, watts, or I could put 75 kW. Then I know this angle, right? I know this angle would be what? Here I got to go up to this. I have to take the inverse cosine of 0.94. And what do we get for this angle, people? Anyone? I just need the inverse cosine of 0.94. Maybe I can actually put that up on another screen. Let me just see if I can. Hang on.
It's 19.95.
19.95 degrees, right? Y'all with? Is that right, people?
Was the new angle specified as lagging?
Yes, and it will be in the first quadrant. So this is the new angle, and it's 19.95 degrees. Do you agree with that? Everybody?
Yeah.
Still in the first quadrant because it's light. So what's this new value here?
Could you move your paper down?
Yeah. This is going to be what? Well, it's going to be found by taking the tangent of 19.5 times 75 times 10 to the third. So I could say that Q new would be equal to 75 times 10 to the third times the tangent here of 19.95, just about 20 degrees. What do you get for this? Anyone?
27.2 kVAR.
0.2 kVAR, right? Now, how did we get there? We started with what? 45.45 kVAR, right? I'll put kVAR here. Agreed, class? And we reduced it by adding the capacitor. Mathematically, what you did was add this value in, add the minus J omega C V squared right there to reduce it. So what I can say is the new value, and this is what I'm going to do here. So I'm going to say Q new would actually be the old value, Q old, minus omega C V squared. For my case, it's equal to, this is what I'm after C, so I'm going to rearrange this a little. First, do you all agree that this is true? We have Q old, right? We figured out Q new. Now we need C. Do you all agree that that is correct, that equation? How many do?
So is that, like, what is the symbol you're using for the, is that a Q?
Yeah, and
Or a 6?
yes, it is a Q. I'm trying to say Q new is equal to Q old minus omega C V squared. Do you follow me? The new value of the reactive power is equal to the old minus the reactive power associated with the capacitor. Agreed, class? But we're after C, so what do you see we do here? I can take this to this side and this to this side. So I can say Q old minus Q new. That would be equal to omega C squared. And if I divide this by omega V squared, now I have C, right? Q new is 27.2, so it's 45.45 minus 27.
Joseph, do you think he just lost connection?
Yeah, I'll just send him an email.
Okay.
Just, oh. Can you hear me? I don't know what happened. I got kicked out. I apologize, but I don't know. This happened last time too, I think. All right, are you all with me on this class? As far as the calculations for C. And what did you get for it while I was gone, anyone?
What was omega?
Omega is 2 pi f, right? So it's 120 pi. Does
Does
everybody?
the J disappear from that equation?
It really doesn't matter because C is a real value, isn't it? It has no J in it.
Okay.
So what is the value you got?
Uh, 1.16 times 10 to the negative 6.
Anybody confirm that?
I got that as well.
Huh?
Yeah, I also got the same thing.
Same thing. What did you say, Amanda?
I just said I got that.
Okay. I'm assuming it's correct. You can check in the manual. That is the technique. So the idea is draw a power triangle, find the complex power V times I conjugate, draw it up there. You get that angle in there, and that is the cosine of that angle is the power factor. Now, it's really one of these things, you're going to have something unknown, maybe two unknowns, and they're going to have 2 or 3 statements that allow you to solve for whatever they ask, either the capacitance, the power factor, or whatever. That's the process you go through with these problems. I gave you a bunch of problems that had that, and this is power factor correction. Are you with me, class? How many get the general idea? You're adding a capacitor to make the system more efficient by reducing the angle and thereby increasing the power factor. Ideally, you'd like a power factor of 1, and I'm going to warn you about one thing on the quiz. If I asked you for a power factor of 1, make sure you know how to calculate the capacitor. All right. And any value towards 1, just like we've been doing. Everybody good with this? Now, I'm sorry about that little glitch. I'm absolutely unaware of how that happened, other than either it was my internet service provider or it was something at Auburn's end that messed up. But in any eventuality. And on Friday, there will be a quiz, a short quiz at the end. Got it? Now, last time that quiz was very simple. This will be along those same lines, but you must, and I repeat, you must understand this. And next, I'm going to talk about, now is everybody good at that? Any other questions regarding power factor correction of the previous 2 homeworks? Anything at all from anybody?
Could you explain again why it's good to have a power factor of 1?
Well, that reduces the voltage at the load to its lowest value. Remember, voltage at the source, pardon me. If you want to consume a certain amount of power, then really power is always dealing with a resistive value. Isn't it real power?
Yeah.
Well, any kind of reactance, which increases, or I should say increases the angle, decreases the power factor, that's in series with it, or in parallel with just the load, what it does is require that more current be pumped by, really more power be supplied by the source. I'm saying power, more voltage really, to drive that current to the same value. And that is expensive. So what they do, you always want to get the power factor as close to 1 as possible. And that's the minimum amount of voltage at the source that needs to be created to deliver that power. That's what it comes down to.
Gotcha.
Now here's really what's going on. It's the reactive impedance gets canceled by that capacitor. And you know, if you can cancel the reactive impedance, basically you're not drawing current through either capacitor or inductor. And if you're doing that, then all the current's going through the resistor. Therefore, effectively, you're having the most efficient transfer of power. Without getting into too much into the math, you can look at yourself and appreciate that. I want to do one more. I know we're at 1:52. People have to go. We didn't have a lot of people to begin with, but if you do, thank you. Now, I would like to do one other thing, sort of well, anything regarding this stuff. This is technically an office hour. Anybody? Anybody? I'm really throwing it out there for anybody. I want to say the last quiz, the performance was outstanding. Even with all the zeros thrown in for people that didn't take it, it still was a very high average, and I'm glad that y'all are doing better and better. So now I'm going to ask, is there anything you want me to work before I get into the next thing? All right, I can see not, but this is kind of nice and it's very valuable. How many here that are remaining have heard of three-phase power? Anyone? Man, talk about a thin class. Everybody's jumping. I like the applause. Three-phase power is very important. That's the basic structure of power being delivered by the power plant to really the residential areas and especially to manufacturing. How many here? Well, I bet you some of you are industrial engineers. Just taking a shot out there. All right. If you're industrial engineers, if you're an industrial engineer and you're going to be working at some large plant, and your dream is to run a plant. I don't know if anybody has that dream, but you make a lot of money doing that. There's always, the most money is always involved with people that they can't live without. You can't live without somebody that knows how to run your plant at the highest level. In other words, deal with the power companies and all that. In my line of work, you can't run a business without having somebody that's actually what's called a compliance engineer. So when the product goes out the door to go into the open markets, that you meet all the regulations. Trust me, there's a ton of them by the Federal Communications Commission. Those people are paid enough money to buy a castle in Europe, but they're paid a ridiculous amount, but because they're just irreplaceable if you don't have them.
What's the name of that again?
It's called a compliance engineer in electrical and computer engineering. Now, it's the same way in industrial engineering. You would have somebody who effectively is the same thing that runs the plant. Without that person, basically the whole thing goes down. I mean, they have all the knowledge of how to, reduce the power factor to the, or I'm sorry, get the power factor to close to 1 as possible. They know all about how to deal with the power company and your particular plant. If you put new machines online, if you have something where you're going to do production, some of them are online, they shut down, you got intermittent problems, all that. They're the guys that are the masters of designing the optimal way to deliver power and thereby reduce the cost of operation and hence optimize the amount of profit per hour or month or year or whatever. And that, as I understand it, is something industrial engineers are very good at. And if you're very good at it, then you make a fortune, especially if you're in a plant that does stuff with a lot of power. And I'll tell you, like a foundry, an old mill here, or some of these car manufacturing that's now automated by robots, those people always have the interface to the power company as far as I know. So what is three-phase power is my next question. I'm going to do this in a Mr. Rogers kind of way. I'm going to just try to introduce it in as simple as possible and why it's important, okay? And I'm not going to do this trying to be making it hard. I hope this lecture goes over well. I'm thinking about teaching you guys the way I would my friends' children or grandchildren. So let me just see if I can do this. I'm not saying I can, but let me see. First, y'all see a sharing screen?
Yes.
All right, next. After that, let me see if I can get this up. All right, now here's three-phase power in a nutshell. First, I'm going to show it to you out of this book, and then I'm going to explain it in the easiest possible way to understand it. I'm going to do it just with it's a problem, but don't worry about it. Here's what three-phase power looks like. If you can see by my hand right here, there are 3 voltage sources. Do y'all see them?
Yeah.
All right. Now, in those voltage sources, the first one here is 120 volts at 0 degrees. And there's a center point here. You can actually ground that. Don't worry about this. This is just a little added information. What happens to that is that fundamentally, that's what we've been dealing with so far. We've had a load over here. We've had a single voltage source we're talking about. But the way real power is delivered, and you don't have to write this down, you're going to get plenty of information about this in the days to come. The way real power is actually delivered is there are 3 of these effective generators with the same value of voltage, but they are skewed by 120 degrees. The first, this not 120 technically, but it will be some voltage. It'll be 120 at 0 degrees. This one's 120 at minus 120. This one's 120 at minus 240. Now, the logical question is, why would they do that? And the reason is this in a nutshell. Because now the average power delivered to the load, assuming all the loads are the same and all three phases, all the power delivered to the loads is a constant, and the peak power is equal to the average power. Got that? That's the reason they use three-phase power and not single phase, because then you get something where there's a peak power, then it goes to zero. Peak power, zero. That causes a lot of wear and tear on, well, theoretically on the lines. It causes what's called transitory behavior. In the book, in your book too, there's a lot of information about this, but I want to just make it something that is useful to you. And I'll try to do my best. Now, in his book, here's the nutshell. You just watch this and relax. It's not a big deal. Instead of showing them as a Y, here they have them all on a single plane and they just show the voltage difference. Here's 120 degrees at 0 degrees. There's going to be 120 at...
We can't see.
Right. Isn't going quite the way I want, but I'm going to try my best. But basically you had what was shown earlier, except you take all the power supply or voltage sources and flip them onto a single plane here and have them, you might say, parallel to each other. This should be minus 120 and this is minus 240. That's another way to look at it. Now there's something interesting. They use a common point of connection that's actually grounded. That's called the neutral, that I'll get to next time. And this is going to probably bore some of you, but just appreciate what I'm getting at. They are something called sequences. The first sequence, the 120 volt source at 0 degrees, is just like the voltage sources we've been using. You'll see it's small a here. That's at the transmitting end of the power. And there's a neutral here. It'll be a small n here. Don't worry about it. Then there's the next phase, 120 volts at minus 120, and then 120 at minus 240. They're exactly 120 degrees out of phase. When you go through the math on this, and here's where I end, if you take the first current, it will be Im cosine of omega t minus theta. The second current is going to be the same as the first, except it has 120 degrees of phase difference. And the third is the same as the first, only now it has 240 degrees of phase difference. Don't worry about this. I'll give this to you in a way that you understand in a PowerPoint as well as in a lecture. When you go ahead and take this current and multiply it by the voltage that created it, you get a power here. And that's what he shows here. And when you do this, what you find out is that the average power of all these things comes down to a constant value, and it is the same as the instantaneous power down here. It's 3/2 Vm times the cosine of the angle, and that cosine of the angle is the power factor on the driving end of the first of any of these sources. I'm going to go through this, but that's the reason for three-phase power. Got it? In other words, the instantaneous is the same as the average power. It has the least wear and tear, is the most efficient way to deliver power. Next time I'm going to go through this, and I am going to go through it. And then hopefully when we're done with this, we'll do the delta and Y connections, 1 or 2 more lectures, and then we'll be able to jump into the next major topic, which is going to be transformers or magnetically coupled circuits. Okay, now, I know it's a little slower with Zoom, and I know some of you had a test. Did everybody here have a test? I'm looking at 1, 2, there's 1 industrial engineer. Emma, I think you are, and I think...
Emma and I are both industrial engineers.
Pardon me? I'm sorry.
Emma and Gabby are both industrial engineers.
And Jessica, I think, is too. I don't know about Dylan. Joseph is aerospace, is that right?
Joseph is materials, I think.
Jessica's materials. Sorry. Well, I try. But if you didn't have time to spend or much time to spend on that power factor stuff, please do. And then I'm going to give you some stuff, simple stuff about three-phase power really three phases. And I'll explain this in the most practical way I can. Did you understand today's lecture, test and all?
Yeah.
Yeah.
Okay. I mean, I tried to get at the way to solve the problem. And unfortunately, because I can't see you, I don't know if you're getting it or not. I just have a black screen out there and I see Joseph and occasionally somebody else. I think Gabby, I think you had your camera on and maybe one other person, but I mean, you see what I see, I think, as far as faces. And it is a dismal picture as far as the interaction. But did y'all get it today?
After I've caught up with the notes, yeah. You're going pretty fast at the beginning.
Okay, well, my apologies. Gabby, do you have any questions or any concerns?
Oh, I was just gonna say, sometimes the handwriting for me is kind of hard to tell what you wrote down.
I will do better. Thank you. I appreciate
Yeah,
that.
that's my main note.
I will try to be better about that. Thank you. In my penmanship is terrible. You don't know this, but I've got a torn up right hand. The thing, I've got scars up here. This thing doesn't even straighten out. It's from football. But I can write better. And I will do my part. Emma, what about you? Do you have any concerns, questions, comments?
No.
Okay, I have another question. So we're adding capacitors right now. What would
In
you
parallel.
do differently if you were adding inductance?
You
Like
wouldn't
adding
add
them-
inductance. Not in parallel. Anybody that adds inductance in parallel gets fired. You know why? It's a DC short. All right.
Ooh.
And when you put something up there, there's a lot of reasons for this, but basically what you're doing is giving any DC potential a direct short. And basically that inductor will act like a fuse and blow up. And I'm not going to get into the reason there's the DC offset sometimes, but there is. And you'll see only capacitors used in parallel, the correct power factor. As far as I know, and God help me, I hope now I'm not missing something, but there's nothing out there that would have a leading power factor in industry that I know of, but I'm saying maybe there is, maybe I'm completely oblivious. There's something in chat. Oh, your arrow. Okay, thank you. Anything else? I mean, really, this office hours for you guys, it's not, I've got plenty of things to do with my time, but I'm trying my best on this course because it's a pain in the butt to reach everybody at their level.
I have just like a general class question. Can we have some kind of review session? And if not a review session, could you give some kind of guidance on what you would recommend we should
Topical
review
areas
for the exam?
Yeah, and the nice thing about this course, by the way, is almost everything builds on prior stuff. The exception of that is the transient analysis. In that case, there are transient analysis problems that don't directly relate to the material we're doing now. But everything we're doing now pretty much requires circuit analysis techniques from before. If you think about nodal mesh, Thevenin, all that stuff is applicable to what we're doing now. But right now it's so simple, there's not really any complicated problems. There's single loop circuits, right?
Yeah.
All right. But it could easily, and you're going to see this, especially with when we get into transform, become a little more complicated where you would be using either nodal and stuff. But in general, it's this. And I'm being as honest as I can. If you understand nodal, mesh, Thevenin, check those boxes, you're pretty good. Complex numbers, you have to understand. Impedances, remember, have a real and imaginary part. Remember, all the stuff we started with, we use the peak value of voltage, peak value of current. Right? With power, the recent stuff, it's all RMS because the power company chooses to use that for a lot of reasons. Now, when you do transient problems, you're still using peak values, but there it's only a battery, a DC source that causes the power to either, I mean, it creates the actual initial or final energy state, creates both actually, and a switch just changes the state. So you're going from one state to another, and the mathematical description is pretty straightforward. It's voltage on a capacitor, current in an inductor. And then from those two, you get everything else. Now, one last thing I'm going to mention that's important is that when you're doing the test and the problems, that you have a complete confidence in your calculator's ability to do things. In other words, you're not going to fiddle with it with complex numbers or worry about it in any way, shape, or form. And if you have a complex 2x2 matrix, you can enter that and get the right value without all sorts of angst and stuff like this. What I'm trying to tell you is make sure chapter 4 problems especially, you can do without a lot of angst and trouble. Now, I did not give you a 2x2 matrix to solve on any of your quizzes simply because I felt that in this class in particular, no matter how much I harped about this, people would be lazy and not learn how to use their calculators with complex numbers. You're not going to get a lot of partial credit for the problems with circuit analysis with complex numbers if you don't know how to use your calculators to calculate the real values. And
If we review the quizzes,
sure,
do you think that would be
a very
sufficient
good,
studying?
well, it's, if you go, you should know how to do the quizzes pretty much without, not a lot of effort. It should be, oh yeah, I got this. I've had it before. Usually a quiz kind of slaps you in the face if you mess it up, you don't forget. But then make sure you do homework problems and you can look at the homework and know what to do and why to do it. There should be nothing baffling, is what I'm getting at. The quizzes would be the starting point, and do them without any solutions.
Thanks.
Then, huh?
I just said thanks.
Sure. And the second thing I'll tell you is, and no matter how much I say this, it doesn't work. I have watched, in particular, last time I taught this, watched one particular person. No matter, I said, you know, the hour before the quiz, this person had a problem with anxiety. So just take the hour off, relax. Don't worry about it. Try to put yourself in a relaxed state before you take it, because some of you know this. There's a thing called the primitive brain, and when you're nervous and tense and all that, what happens is you get a lot of adrenaline and your blood flow doesn't go to the cerebral, to the thinking part of the brain. It goes into the primitive areas for survival. And so you will have things like memory lock or memory block. You can't remember things. You can't, because you're so wound up with adrenaline. And the worst thing to do, and I have a story about this, is to get yourself all super jacked up on caffeine or speed or something like this. God, I've had encounters with kids where I thought they were going to have a cardiac arrest because they literally come in so jacked up on stimulants and then they completely blow everything. One kid in particular, I think he was taking Adderall, but I don't remember. He told me, oh, I got this. And I good. He's basically made a 0. But he was convinced he just aced it. And that's what happens when you get too much stimulation before an exam. Try to relax and sleep as much as you can the night before. Now, that's my advice. I know it's not easy, but there are all sorts of things on the internet about breathing techniques, relaxation techniques that'll help you, especially if you suffer from test anxiety. I don't know if you do. When I was where you were, I would make it a point. I had a German professor named Hagenbuch who told us, now before the exam, don't do anything. It's the best thing you can do. And I used to think, yeah, well, now he's assuming you did the right stuff the night before, but by God, that worked. It really does. I don't know. I mean, you guys are juniors and seniors. You've been around the block. You've had a lot of tests and stuff like this. I don't know if you still have test anxiety, but I've had kids in my senior courses that still had a kind of a problem with it. And it's a real problem. You know, they get wired up the night before, they don't sleep, they come in, they're all jacked up on stimulants, and then their performance is horrendous. So that's what I've noticed.
Well, I had a problem with that from Honor Lock. It was
Honor Lock.
for another class. Dr. Birch's class.
Oh, God.
I've never been so angry at a test in my life. Every time I shifted my head slightly, it would, fly, the whole screen would blank out and it'd say, return your head to the testing area, or and we'll show you your test again. So like every time I look down to write down some numbers or to look up something in the Steam tables, I'd blank the screen, and then I was screaming curse words. Supposedly they could listen to you. I hope someone felt bad.
It won't
But like
matter.
I wasn't moving. I have no idea.
I won't use honor lock. Matter of fact, my dog. I have a dog. She's a greyhound, and something out back got her riled up. What are you barking at? What? Anyway, I wanted to tell you, if I can help you with anything, I will, and I try to give you advice that's practical from my end. I mean, my big thing was if I studied, and I studied the way I told you when I was in your shoes, I would go into a test, and I don't think I was looking forward to it more than being afraid of it. I used to want to get in there and weigh into that test and get out of the way, because it was almost something I just want to put behind me. It was, I'm ready for it. Give me it. Sort of like if you ever, I mean, if you ever did anything, sporting events or anything, when you're ready, you want to get it out of the way. Anything else?
I have one more thing.
Okay.
So I was looking this up. I spent forever looking up how to do a simultaneous cloud recording and local recording. And so I have one idea that might work, which is if you, instead of co-hosting me, you can go to, first you'd have to unco-host me, but then you can go to the place where you normally the ... and then give permission to record or allow record.
Sure, I'll do that next time. Just remind me.
I want to try it right now to see if it would actually work.
All right, I'm going to withdraw permissions for you to be a co-host. Then I'm going to go to the ... as you said. And let me see if you can see what I see. Hold on, since you're on here. Can you see that or not? Can you see where it says mute video? Do you see the cursor?
No, I do not.
See it now? Or not?
I see the cursor, but I don't see the.
All right, now look, do you see anything that says mute, stop video? No?
Like I do on my screen.
Okay, well, I see chat. When I go to ... I see chat, breakout rooms, pause recording, stop recording, close caption, hide video panel, hide floating media controls, share computer sound, optimize share for full screen video clip. I don't have anything.
Oh no, I meant to like on where you would give me permission, you would click on if you can mute the participants.
That's participants. Yeah, I got Joseph Sanders. Yeah, it
Like
says more.
on my video box.
Make host, allow record. I can do that. Can you record now? I hit allow record.
Yes. And I think that's a local recording instead of a.
Well, you want to put it to a cloud, you probably can.
I don't think that students have cloud permissions. The only reason
no,
I would
you
be
can
allowed
put-
to start a cloud recording is because you made me co-host.
I can tell you that people put this thing on YouTube all the time. They don't record it to the cloud with Zoom controls. In my other lectures, they were putting them all on YouTube.
Yeah. I couldn't figure out how to start once you had started a cloud recording, I couldn't figure out how to start a local recording.
Well, Jessica messed around with this. Didn't you, Jessica?
Yes, sometimes you have to like stop the recording and then play it again and start recording again. If you join and he's already recording, I like pause it and I record again.
Okay. I hadn't tried that.
Try that and see if it works too.
I was worried that if I hit stop recording, it would just stop the whole cloud recording.
I'm not sure if he had stopped in the past, but I did that in the class. And he was
Okay.
hopefully it didn't.
Well, hopefully that'll work going forward.
Mm.
Because currently I think I'm making a local recording. Stop.
Or before Dr. Baginski started the cloud recording, if we become host and then we started recording and then he starts the cloud, I think that's fine too. Because if
Okay.
you start first, even if you start.
The allow record only allows me to do a local recording, so I was able to make a local recording just now.
Okay.
So I have a .mp4 of the past minute.
I'll tell you one thing. If you want to record it locally on a terabyte drive, you should be able to load it to YouTube.
Yeah, I'll do so. But if like,
But
so
this is my take on it. YouTube. They never erased. I've got stuff on YouTube from 10, 12 years ago where they've recorded me. Matter of fact, I'm just kind of curious about one thing now that what is this? When I'm curious about one thing. And there's so many people that have recorded my lectures and put them on YouTube, and I'm glad because it helps students. I mean, that Zoom stuff's going to be gone in no time. They're not going to keep it up there. But YouTube will keep it there forever, which is good. I mean, if you look at the stuff on YouTube, there's stuff in there from long ago from MIT, Stanford, all those places that are fantastic. So I'm happy about that. Anyway.
I was looking, apparently Zoom by default deletes all cloud recordings after, I think, 7 days or something.
Is that right?
I'm guessing that the administrator from Auburn has either paid money or enabled a setting so it does not do that.
Let me tell you what I think we should do, and I mean we've got we got the month, we got 2 weeks at least in October plus the rest of November. We should think about just making sure it's always on YouTube, all these lectures. That way, no matter what, you can go back.
Okay. So I'll see if I can download the previous cloud recordings and put them to YouTube. I don't know if that's possible.
All right. Hey, Jessica, I got a question for you.
Yes,
when are you headed back to Portugal again?
probably in December. I would either go to Portugal or west of Africa. I also have some family there to visit.
Well, and you'll be able to get back into the country?
Yes.
I'm glad to hear.
Before, during the summer, they had come up with a law that if you're not taking in-person classes, then you can't stay, but then you can now. And I think for next semester, most of the classes are going to be in person.
Boy, I talked to the provost about this the other day. This is the dilemma. Students, and I'm surprised in this class, the majority don't. The majority of students that are polled want in-person classes. They are not happy with Zoom, and I don't blame you one bit. If you poll the professors and they're honest, well, I say this, there are some people out there that might rather have Zoom. They would rather be in person too. If I have a board and a class, I can do more in less time, and it's more, I'd say, clear. And I can look at you and tell if you're getting it or not. Now, this Zoom business, the real problem is participation. If I had everybody, I've had one class like this. It was a smaller class, it was a major, and it was graduate too, where it was radar. I had people in person. I mean, I've had the Zoom thing in the spring, but everybody was on it, and I had a very animated class. So they would challenge me on points, and it was like an in-person class in so many ways. This class is massive. If I see 10% of the people with their screens on, it's a miracle. Very few people will turn them on. It's very hard for me to figure out if I'm communicating or not with the audience. It's just tough. And participation is a key. And you would see, now Joseph, you probably and Jessica get more out of this class than 90% of the people in it, simply because you communicate. If you don't understand something, you'll ask. If papers off screen. You're going to let me know. Anything I'm doing that's a bit odd, you'll let me know. I don't know if these people are even on. I mean, really. I see there's a black thing out there, a Hollywood square with their name, but there's no evidence of life.
Like you're paying a lot of money to learn this material.
Well, the funny thing is, and I mean, this is my philosophy. When you were in high school, when I had to take like phys ed and health, to me, it was a waste of time in a lot of ways. I played sports in high school. Physical education is a waste of time. I did more physical education than I wanted to most of the time. They made us take health, and I think it was health. I forgot the name of it. I just wasn't into it. I was into my science and mathematics courses. Things like great books, It's Hot and Cold. I loved Hemingway's Old Man of the Sea. But some of the other ones, okay, there's an appreciation you develop for Shakespeare, but when you're a 10th and 11th grade kid who's got sports and everything else on his mind, guys, they just don't have a natural inkling towards Shakespeare in general. In college, you will. But this ain't high school. You're paying good money, and those grades are going to be reflective of your position in the world in years to come. And you got to learn this stuff. This is not organic gardening. I mean, this thing right here is something you're going to have to probably know at some point. Not everybody, but plenty of you. But I don't get that here. When I was, when I was at Penn State, there's always partiers. Doesn't matter if you're at MIT. There are always people that are there, and their mode is, I'm here to have fun, and they're going to go to football games, basketball. They're going to go to parties and all that because their parents are probably rich. Now, if daddy's got a place, you're going to get a place to work, then it's one thing. But if you're going to have to fight it out in the real world, God help you, because you're not going to be a medical doctor unless you can pass those boards. Doctor and no daddy doctor. I mean, to really get in, you have to show fairly high scores on the MCATs. You have to show proficiency. You have to get good high grades in school. There's a lot of requirements. A lot of people come out of college that spend it partying and really have a huge amount of regret. And I've seen that with my own eyes plenty of times. But if you do your work and try, and really, it may not be the most enjoyable thing, but try your best to enjoy it and learn it. You're not going to regret it.
You're paying like you said, you're paying a lot of money to, like, the grades you get are proof to an employer that you understand the material that they're paying you to understand.
Well, it's supposedly a seal that you have at some point understood the material well enough to get through that class at the level of grade you're given. Now, what they're doing now more and more is when they hire somebody, they're actually giving you an aptitude exam. And I can't speak to what they all do, but places like Intel, what they'll do is, well, you're versed in electrical and computer engineering. So basic circuit analysis techniques, transients, those are things you should know. They're no-brainers. I mean, they should be as like F equals MA if you're a physicist. That's a no-brainer. You have to know that. You have to know a certain thing. So, and especially with a lot of the digital stuff that you don't need to know. You know about Arduino and some other things with microcontrol. But whatever it is that would be considered base knowledge, they're going to test you on. Because they got people at times, and I'm not joking about this, that come out of colleges, good colleges, that somehow organize their courses to take professors that allow them to get through almost scathing without anything. And they know. My brother is a guy, he told me a story that, and this is at Huntsville. He was working for, I think it was Sanmina at that time, but I'm not sure. Anyway, he told me that they had hired a 4.0 Auburn graduate, I think out of business. And they gave him very basic things to do, and he was horrendous. I believe it was him. And he said, no more. From now on, we get anybody from Auburn University, period, we're going to go ahead and he went to Penn State, same as myself, give him a set of base questions to answer. And based on the response, we're going to figure out what we're going to do as far as an offer, or if there is an offer forthcoming, because you won't believe the garbage kind of stuff that these people have to deal with. And you know, most employers that interview here, good ones, you can't get an interview unless you have a 3.0 or better in your major, usually, sometimes just overall. I think you guys know that though.
Yeah.
There are exceptions. I mean, if you're like a 4.0 in your major and a 2.5 overall, they'll probably have a lot of forgiveness in that case. But
I had a 3.0. I got a concussion and
well, that's a medical problem. They can understand. They cannot understand somebody that's here that doesn't play sports, that and doesn't have any other problems coming out of here with like a 2.8 or a 2.0 or a 1.8 and then trying to interview and expect to get an interview. Maybe there are exceptions, but those are rare ones. And for the most part, Auburn is a good, solid college. You come out of here, you're well trained in electrical and computer engineering and in engineering, as far as I know, in general.
I have an anecdote that I heard back when I was in biosystems. You had to take a bunch of biology classes. And the memo got around that a student who went to UAB, their medical college out of Auburn, like they went to UAB Med School, which is a very good competitive med school.
It's a very good school, ranking-wise, yes.
And so they were in one of their first labs. And they had, once this got back to the Auburn professors, they were horrified. This student who had very good grades, when we get into UAB to begin with, could not recognize what a human heart looked like. Like he didn't know what an actual, like I guess they'd seen diagrams, but they like presented with the physical organ that looked like a heart, they could not recognize it.
You know that this is the truth, that it's not made for TV kind of stuff?
I know it's true because they said from that point on, they added to the curriculum, they passed a cow heart around and they said, this is, you know, you cannot pass this course without being able to recognize this, handle it, and it'll be part of the lab practical.
Well, you know, at one point I was going to be a medical doctor. And this is very strange because I was in there with all these guys that were, it was called the Hahnemann program at Gannon College. And I needed to take some courses that summer. So I took a year's worth of chemistry and a year's worth of calculus in 10 weeks. I'll never forget that. That was the hardest semester of my life. I didn't do anything. Friday night I was working, Saturday all day I was working basically. I think I went to a prayer meeting on Saturday night. I'll never forget this. This is such a crazy thing. I was exhausted at the end of the first 5 weeks. We had a short break. And I was in with the pre-meds. Now, if you're admitted to that program, in 5 years, you're a medical doctor. You do 2.5 years of undergraduate. And you take 4 years and 2.5 years. Basically, everything's condensed. The amount of credits are way up there. You get no summers off. And to be admitted, you need very high SATs or ACTs. And I forget how high. Anyway, I ended up in there with these guys. And when I went to college, I paid for a lot of it. And I was very, very competitive. And I wanted to learn everything. Well, I did very well. And I was like, you know, maybe I'll be a doctor. I'm not really into medicine, but, you know, these guys make a fortune. They talk about it all the time. It's the highest paid curriculum that's non-business, you might say. I mean, the highest paid thing, if you're going to be a bank, if you have the fast track to a position in banking where you can be an officer, you're going to make a fortune. But those are few and far between. That's business. But in general, the highest, and when I was going through at least, the highest average salary in the sciences and anything like that was in medicine. And it still is very high today. So I kept hearing all this and I'm thinking, well, I can be a doctor. I could learn to enjoy medicine. I'm not a real fan of, you know, learning a whole bunch of terminology with organic chemistry, but I can do it for money, I suppose. Well, my neighbor, thank God, he talked to me. And he said, why do you want to be a doctor, medical doctor? Well, they make a lot of money. You don't think engineers make money? Well, they make more. Because Mike, you're missing the whole thing. You're going to make plenty of money as an engineer. You're going to make plenty of money as a doctor, but you're going to live as a doctor for the rest of your life. You can't be a doctor and jump to be an engineer. And I'll tell you right now, there's not a lot of people that are in the medical profession that absolutely love it. And there's a lot of suicides with dentistry and stuff like that. Those are people that can't be doctors, a lot of times become dentists. And there's actually truth to that. And I have a friend who's a dentist. He's actually an orthodontist who went through that because he got an F in a course in basic chemistry because he was dating his to-be wife and they had a terrible falling out. And anyway, he couldn't get over it. Very bright guy. He's from New York. He's Jewish. Anyway, he got one F and he didn't think he would ever get into med school. And he didn't because of that. He got into dental school. He's a brilliant dentist. And anyway, I'll never forget this as long as I live. You make one F, it's the kiss of death. At least it used to be. You're never going to be a medical doctor. You might be a dentist, but not a medical doctor. So that was his story to me. And anyway, he loves what he does, but he's a rarity. Many, many doctors and dentists, I'd say, did it for the money and may regret it. They don't regret the money, but they regret sometimes what they have to deal with. Now, some people are just natural. They're naturals in that area. I love engineering. I love science and mathematics. I love making things and I love figuring things out. I love things like chess. If you don't have that natural gravitate, that draw to this kind of stuff, and you're doing it for the money, you're going to hate yourself.
Yeah.
If you look back how you got into the field you're in, you might be surprised how very little it took to get you there and what could have got you out. For me, it was a course in high school in electronics was the single thing that drew me into electrical and computer engineering and really into the area I'm in now. That was the one thing. And I think about how little it takes to get people in certain majors, like business, like pre-law and stuff, I guess, or medicine. It's not a lot. And if you look back, I bet you it's not a huge amount that really got you where you're at. You could have gone many, many different ways.
Yeah. The only reason I picked biosystems to begin with was because of I went to this Envirothon, which is a for a Alabama outreach thing when I was in high school, where it was just like an 2 days environmental competition where it was like extremely long, maybe 14 hours of intense lectures, and then you get tested on it at the end, and then you had a big project the next day where your group from your school then would compete against others, and you present this like sustainable farm thing. And I didn't necessarily like it at all, but I was really good at it. And I thought, well, I want to make money, so I don't want to be a scientist, even though that's interesting to me. So I wanted to be an engineer of some kind, and I figured, well, why not be a biosystems engineer? It's close enough to what I was doing in high school. I was good at it. And I took a mechanics and materials course and found out, hey, this forces and stresses and how stuff bends is under great pressure, and how the molecules slip apart like out of their slip planes, the actual mechanisms of strain. That's incredibly interesting. I've spent hours.
Have you had your course in crystallography?
Not yet.
I'll tell you one thing. I did my initial graduate work was in solid state physics / electrical and computer engineering, but I took a lot of stuff, crystal chemistry, crystallography and stuff like that. I'll tell you, some of the stuff coming out nowadays with these exotic materials, some are amorphous, but a lot of them are crystalline. Now, crystal stuff is very interesting because if you look like graphene, have you ever heard that term, graphene?
Yeah.
You know what diamond is? It's the hardest material.
Yeah.
Diamond, it can also be turned into a transistor that has enormous, unbelievable benefits. The problem is you can't create a transistor easily. Matter of fact, it's almost impossible to create a transistor the way it's normally done without getting into too much, because it has to be crystalline. And as soon as you do something called ion implantation, you put impurities in to change the electrical parameters so it'll act like a transistor, then you have to do something annealing it where you're going to recrystallize it. You need unbelievable amounts of pressure to do that part. All right. You can make synthetic diamonds, but synthetic diamonds that can function as transistors are ridiculous to make, and they're so expensive they're not worth the time. But now with these exotics coming out, if you are material science, there's one guy you should look up. His name is Jim Tour, T-O-U-R. His name is James Tour. He's whatchamacallit, he's down at Rice University, super brilliant. He's actually a synthetic organic chemist by trade, but he's doing tons with nanotechnology and synthesis of things like graphene and all that. Read about that if you're a material scientist. You want to see some wild, out-of-the-box kind of ideas that they're working on. He's the kind of guy that's doing stuff that the military is doing, in my opinion, behind closed doors and will never admit to. I mean, he's doing it out in the open. And I don't really know, just my little bit of knowledge about the military and the little dabblings I've done. Anytime something is really a hot idea and super, like a nuclear weapon, nobody knows you're working on it until it's made. And that's sort of the thing with some of his stuff. It's got a military application, so I'm certain they're doing it. And nobody will ever know they're doing it. You don't know who's doing it. And it sure ain't MIT and Stanford anymore after they blew it a few times. But
like even here at Auburn, like before last semester kind of fell apart, or not summer, like the last spring where the pandemic happened.
mm-hmm.
You know, I was taking a materials class with my professor. At the time, he offered me a job as a lab assistant. I didn't take it because at the time I was taking a lot of courses, and suddenly I wasn't taking any courses. But he was talking to me about, like, they do, even at Auburn, they're talking about nanomaterials where they're moving, like, one atom, or
it's amazing,
like a different crystal phase.
If I could find this thing, graphene. I mean, guys, this is one of these super geniuses. He's just not. He's at a different plane. Let me find what. I love this guy too. There are certain people you run into in the scientific community you can relate to that are just so far above everybody else. He's one of them. I had a few that were on the national academies when I was in college, and it was always a blast talking to them because they were so transparent. Where is that? I think this might be it. I'm going to send it to you in 1 second. Come on.
It shows you how when we water etch, you can see that we can double the capacitance just by doing this water etch. So we will pick a few.
I'm going to put this in your chat window, and you can look at it. And this isn't the one I'm really looking at, but I mean, the one I'm trying to find will take too long, I think. Or just, you can go ahead. That's Jim Tor, and this dude. There's very few people that cross so many boundaries. He's a professor in computer science, computer engineering, pardon me, or computer science. In chemistry, he's a professor in something else. And he's one of these guys that he's a Renaissance man in this area, but he's unbelievably brilliant too. I had one guy, actually two, that run the national academies. One was named Rustam Roy. He was from India, and he was a materials guy. And the other guy was Leslie Cross, and he was an electrical and computer engineering. That was material science. Unbelievable brilliance. And, you could sit down and have a conversation, and they weren't trying to wow you. They could, in fairly straightforward way, give you unbelievable amounts of information about certain topical areas. Then I had professors from Germany that always used to scare me. Because You know, European professors in general are like gods. And I don't know if you know that. Jessica, you might actually know this.
Yeah, I
I
do.
mean, they are deities. They are super bright, and they've always been super bright. They've always been recognized for their intelligence, and there's not a whole lot of them. Um, and you probably know this, that if usually these guys, especially in Germany, they have their own lab. You know, if you're a professor in Germany, you basically are given a lot of state money to do all sorts of research, and you have to be very good. I had a couple guys from Germany. One in particular, he was Jewish. His name was Feuchtwang. Excuse me. I knew this guy. The other guy, I'm trying to think of his name. And I probably should tell you this, but I won't. So this guy, I took him for modern physics. So it's after you get done with your basic physics courses, your year's worth of physics. This is things like quantum physics, relativity, not the deep general relativity's applications, but just general relativity, going through the concepts and everything. So, and tunneling and all this. So it was in a class early in the morning, like 8. And I came in one morning, so I always sat in the front, and I was really tired. I don't remember exactly what it was. And I was just about asleep. I thought I got to bed at about 3 or 4 in the morning. So I'm just about asleep, looking for coffee, didn't have. And so he decides it's time to pick on him. Because he'll look at you and point at you. Say, so, and I remember something about this differential equation, and I think it was in cylindrical coordinates, but frankly, I don't recall the exactness of his question. But so, he's got this heavy German, he's looking at me. Well, are you stupid? Literally, and you know, the thing about it is he's right in doing that, because that motivated me. I'll never come in there not understanding what's going on, not having a clear grasp of the homework, because he would call you out and beat you. And the other guy, Feuchtwang, in a way, I'm glad I didn't have him. See, in Germany, they do what they want at that time. If you're a professor, if you want to run your class for an hour and 15 minutes, you do it. If you want to run it 2 hours, you do it. It doesn't matter what the schedule. They really are, they're gods. So his class would always run 15 minutes over, always, no matter what. And he's extremely good. He's a brilliant guy, quantum mechanical guy. So Feuchtwang is a material science, quantum mechanics, physics. So what they decided is, because this guy was really wearing him out, they're gonna set the clock ahead by 15 minutes. All right. And it's in the back of the room. He never looked at it at the beginning, only at the end. So he starts looking. And he's looking at his watch, and he found out about that. He found out what was going on. Man, that class needed to get better to die. I'm so glad I wasn't in that class, because if they thought they got homework before, they'd never had homework. Remember, he's German. He can inflict pain just by thinking. And that dude, Feuchtwang, just had it in for those guys. And you know, the thing about this, when you're in grad school, see, if you get anything lower than B, you can be thrown out. And I mean, you can lose your fellowship, you can lose whatever you have in a heartbeat. And if you're in physics especially, now if you're, I mean, he can just go to your department head, the department said, this kid's not worthy. And man, that's amazing pressure. Don't ever get a prof mad. That was the upshot of the whole thing.
That's scary.
Hey, did you ever have, Jessica, have you ever had professors from Germany or anybody from like Austria, any of those countries?
No, I've had only Italian and Portuguese.
Well, Italians can be that way too, though.
Yeah.
They're real exact, right?
Mm-hmm.
I frankly, I don't have a lot of experience with Italian. All the professors I had plenty of American, then tons, not tons, but a lot of Asian. Right?
Mm-hmm.
Not a whole, not like now, but I mean, maybe 15, 20% Asian. But I mean, you get these English and German people. We had one guy, oh God, Pete Thrower. And by the way, they're brilliant. They didn't come over here because they couldn't make it. These guys are really brilliant.
Mm-hmm.
It was during Princess Di's wedding. This is a long time ago, Princess Diana. He had a Union Jack up on the wall. I mean, these guys, they go crazy. It's like soccer if you got Latin professors around there with their flags, you know, if it's from Brazil or whatever, you're going to see the flag of the nation flying because they want to show. Well, that's the way it was with this Princess Di thing. And do you know about tea in England? Do you know about, they have a tea at 4 o'clock. They have tea time. Right?
Yes, I know.
It's a religion. I'm telling you, it's a religion for these guys. When it's tea time, that's it. There's no work. Basically, don't bother me. And they love cookies. That's the other thing I remember. He'd literally come to our office and look if we had any cookies. If he didn't, those are good old days though. I miss those in a way.
Dr. Baginski, normally the midterm, how many questions will they have? Like 5 or 4?
There's usually 4 major problems, and there'll be multiple parts. Think about a quiz. There's usually 1 or 2 different things I ask about each problem, right? On a midterm, think about a quiz problem, right? I might ask for the power dissipated by a resistor, the complex power used by the system, what capacitance value would be needed to make the power factor at the load change from, say, 0.7 to 0.9 and still have it, you know, lagging. Something like that, where if you know your stuff, you got no problem. Now, I'm not going to do something dastardly or give you like a 3x3 matrix and I ask you to solve, I mean, a problem that requires, that most 2x2. But usually, if you know, if you have a problem where you have just like chapter 4 problems, I could still ask you the power dissipated by a resistor, right? But there would be 1/2 I squared R, where I would be the peak value. And I could ask you things about that. If you just look at the homework problems, they're pretty representative of anything I'll ask. And if you look at your homework, you're going to see the quizzes pretty much were taken from the homework with some adjustments, you know?
Yeah.
If you look back at your old homework, you're going to kind of laugh at how easy it is now. I mean, the old quiz problems even. Take a look at them. I'm talking a long time to you people, and I shouldn't be, but
so
hopefully I'm helping.
Speaking of German professors, I had a math professor called Peter Mink, Dr. Mink. He's a math professor here at Auburn.
I don't know.
There is one at engineering. I think, Dr. Ulrich, something like that. He's Germany. He teaches Cal too, and he's very, very strict. Yeah.
Yes, and by the way, though, I will not, I say this sincerely, I do not regret any of those guys. They were fantastic. I learned a tremendous amount. But man, there is no forgiveness.
Yeah, same with him, like no forgiveness at all.
If you're stupid, I mean, when he called me out that time, I'll never forget it. That was the last dang time I ever came unprepared.
Dr. Mink, I remember the first day of class, he said, I run my own server. I hate Canvas, so I run my own server.
I know that feeling. I know
and at the end of your grades will be calculated by my server. That's where they'll be kept. That's where they'll be calculated. And then I'll post the final grade to Canvas. I might be nice, but my machine is merciless. Those are his exact words.
Here's the funny thing about grades. I get questions about grades all the time. Now, I have to sign a form, your final grade form, all right? But the grades are calculated by the grader in my classes. I give him a grading sheet and all that stuff. And when I look, if I see, an obvious skewing one way or the other, I make adjustments. I will on some of those quizzes. I do. And I pretty much know what's reasonable. But there are certain times when you will get a class, if you ever teach, remember what I'm telling you, that are just people that have, that somehow got together. It's this rare thing where you got most of your class are really bad. And there's nothing you can do to help them. I mean, they either won't do what you say or they don't have what it takes. And they're very bad. And so there you have to, despite the fact 25 or 35 or 45% may fail, you have to make that hard call. I have never had to do the 75% or the 66% that my friends have. But I'll tell you, most of the time, especially a large class like this, you're going to see the percentage of A's, B's, and C's are pretty much the same as the people in their majors get in their major. Pretty much. Not always. You get people that will do extremely well in this course that in their majors, they're not doing that well. But you'll also have people do extremely poorly in this course that are doing pretty well in their majors, but that's the exception. And it's true, because usually you're going to put the same amount of effort into this course as you would others that are similar, pretty much.
Yeah.
But people like Birch can burn you alive because his are all multiple choice. And if you aren't sharp, man, you could fail that course in a heartbeat.
The first test, I got a proud 4 out of 10. Admittedly, the problem was he misworded one problem, and then he had 3 subsequent problems that were based off that one problem. The problem that everything was based off of was unanswerable. So we had to do a retest for the whole class. But he made that retest optional. So he said, whatever you make on the retest is going to be your grade. Or you can keep your first grade. Like if you got lucky and guessed the right answer. Apparently someone I was talking online made an 80 through guessing.
There's a statistical chance of that happening. I myself dislike multiple choice tremendously, mainly because it doesn't represent the student's true ability. You can cheat on those things. There's ways of doing them things. And I have learned that there are decent students, very good students, but there are some. One kid I had, I'll never forget. That kid tried cheating no matter what. Another kid, oh God, can you stop the recording? I don't want any record of this, if you don't mind.